Awesome. Hi, everyone. Welcome to today's RAL seminar. Our speaker we have today is Dr. Ruben Imhoff, who's visiting us from Data-Scarce in the Netherlands. Ruben is a hydrometeorologist with an expertise on precipitation nowcasting, hydrological modeling, and the use of remotely sensed precipitation products in operational water management systems. Ruben got his MSc and PhD degree at Wageningen, I didn't say that, okay, University in the Netherlands, very Dutch word. And within his research, Ruben investigates and evaluates short-term precipitation forecasting techniques, especially with a focus on the added value for the hydrologic predictability in operational water management applications. A main operational focus is the architecture and implementation of short-term rainfall forecasting systems for quickly responding catchments in urban areas. In this field, Ruben is also involved in the development of the open source nowcasting initiative called PySteps. Ruben is also part of WMO's World Weather Research Program Steering Group, Integrated Prediction of Precipitation and Hydrology from Early Actions, or IMPRA, and is a co-chair of the WMO's task team Plan of Action for Hydrology Research. So welcome, Ruben, and take it away with your talk.
Yeah, thanks, Aaron. Well, that makes it easy for me to introduce myself. This is perfect. I'm indeed going to talk about this range of things, so from the short-term rainfall forecasting to the hydrological application, with a focus on seamless rainfall forecasting for the Netherlands. And then we'll end with some case studies for data-scarce regions, because that's where we, at least together with Aaron, hope to collaborate as well. So who am I? Aaron already introduced it extensively. I have a background in hydrology and meteorology. My colleagues are all hydrologists, and they see me as a meteorologist. When I'm among meteorologists, I'm the hydrologist, so that's kind of my position, I would say. I have a PhD in rainfall nowcasting, so that's what I will also be talking about a lot, I think, today. In my current work, I mostly work on flood early warning systems. That's what my department at Data-Scarce does, the so-called Delft View systems that we implement worldwide. And that's for us a great vehicle to do research as well into rainfall observations and forecasts, hydrological forecasts as well, obviously, and the whole early warning chain, so including what to do with uncertainty, not only in visualizing uncertainty, but also how to cope with that in a warning chain. Together with Aaron already said it, we're part of the steering committee IMPRA of WMO. So you see a picture here at the bottom right of, I think, 80% of our group, something like that. And the other thing Aaron said is that everyone in Boulder is always talking about their hobbies, so I have to introduce mine as well then. Here at the top right, you see a picture of it. It's gliding. It's one of my hobbies, but I would say the nicest one to introduce, so that's what I like to do. Hope to do it in Boulder at some point as well, but never had the chance. So what I will be talking about, first, why the need for improved rainfall forecasts. Of course, a bit preaching to the choir here, but just to set the setting a bit or set the scene. Then what is nowcasting and why we use it? For some of you, probably something you've already heard extensively. For some of you, maybe new, so just go through that rapidly. And then we dive into seamless forecasting, so how to combine nowcasts with NWP and the applications of that in data-scarce areas. So why need for improved rainfall forecast and short lead times? So we'll be talking about today a lot is the whole flood early warning chain. So from monitoring all the way up to taking action. Most of the talk will be focusing on really the first part of that. So that is monitoring and forecasting up to the notification of what is happening. I think within IMPRA, we're trying to tackle that whole chain, and especially also focusing on what do you do with warnings and actions at the end, which is, I think, something we can still work on much more. But in this talk, I'll leave that a little bit for the last bits. So the limitation of NWP models, why do we use nowcasting? Especially if we look on the short term, NWP models have the trouble of having quite a big latency sometimes. It depends on the model and whether it's a rapid update model or not, but we're talking about a latency of an hour or sometimes 3 hours. But that means that if you're in severe convective conditions or at least in flash flood situations, you're lagging behind on the actual situation. And it also means that your whole data assimilation scheme, even though it might work well, it is 3 hours behind at that point. And it especially means for flash flooding that you might miss the peak of the flood if it's happening in the coming hours. Now I'm showing here a difference between radar observations on the left and NWP forecast on the right for like the northern France, Belgium, Netherlands area. This is quite an extreme case where NWP was quite off. That's luckily not always the case, especially with the good rapid update models we see doing much better. But this was a case where in the red square we actually had flash flooding. And just to visualize it a bit in the bottom right, you see what the difference would be just schematically between running it with actually having the observations in the NWP forecast at that moment. On the real large scale, the NWP forecast was still good, especially if you would look hours ahead from here. It was not a bad forecast, but it's really those first hours where it just missed what was actually happening on such a small scale, because the Netherlands, the country at the top, is about the size of Maryland. So if you look at that red square, we're looking at small scales. So to also show you a bit how what happened in real case scenario, I'm still focusing here on the Netherlands-Belgium area. We work a lot together. In July 21, we had very heavy floods. You may have seen it on the news here as well. There were quite deadly floods, flash floods in both Germany and Belgium. We were relatively lucky in the Netherlands with no casualties, but lots of damage. There was a lot of rainfall that fell. Nothing extreme for what you could see in some parts of the USA, with maximum amounts of around 200 millimeters within a day. But it fell on an already completely saturated catchment area. It had been raining all month compared to this year where it's super dry. So it went entirely wrong. Now we checked the forecast for the day, and actually the NWP forecast for the day was surprisingly good. We saw it coming days in advance. So for the larger rivers, and that was the luck in the Netherlands, because we in the end get the water flow from both Belgium and Germany into our larger river systems. We knew days in advance that something was happening, we could prepare. But if we zoom into the smaller catchments, and this is one of the 3 catchments where the severe flash floods took place, all of a sudden we miss it. And it's not because the larger system was not forecast right, it was really there, but it was just wrong in its location, and just wrong we're talking about 50 to 100 kilometers off. But on a time scale of 3 to 6 hours, that meant that in black you see the observed discharge peak, and in green what we would forecast with the NWP system we had available at that moment. We missed the peak, and that is something we want to prevent in the future. So that is really in a nutshell why we want to move to a different, very short range rainfall forecasting system, combining also nowcasting and as many observations as possible. So the objective is kind of twofold here. We want to improve the forecast for the first 12 hours ahead, so really that kind of flash flood timescale. And we're still talking about precipitation and principal rainfall here. And the second beneficial point is that if we do this well, we can also reduce the amount of products we're using on that timescale. If we can combine them, that's where we go into the seamless domain. We can make our end users work with one product instead of many. And that is also advantageous for them, I hope. So what is nowcasting and why should we use it? As said here, for some of you, this is nothing new. But just in a nutshell, nowcasting is basically using the most recent observations and extrapolating that in the future. Different ways to do that. I'll get into that soon. But in the true basics, it's an extrapolation, which makes it really fast, but you're not including any physics. And that also makes it very limited in what you can do up to the future. So a nowcast could provide a skillful forecast maybe 2-3 hours ahead. In convective situations, even less. And after that, you just need physics to say something about the future of the weather, of course. And that's, I think, really the difference between NWP, which takes that into account, and nowcasting. So nowcasting really benefits from the latest observations. If those are good, you can extrapolate them. And then you're more on track than NWP is for that time scale. Now, how do we make it? We start with most recent observations, 2D rainfall fields, or 3D if you have them, typically from weather radar, but could also be from satellite imagery, for example. First thing we do is determine the movement of the rainfall field. So we're getting so-called motion fields out of that. And that's what you see here at the bottom. It's kind of tracking where rainfall has been going in the past, so in the past hour, for example. And it gives us an estimate of where it might go in the future. That's something you do by eyes as well if you look at it, and luckily computer algorithms can do that as well right now. So that's step one, and just to stop there, this is also where you can stop. So a simple, just advection-based nowcast does only this, and then extrapolates to the future. That's a very simple nowcast. And then we can make it a touch more advanced. So we can add rainfall evolution, so growth and dissipation of rainfall cells, You can do that based on observations, so you can look in the past and see whether a storm cell was growing or dissipating, for example. You can also do it statistically. That's what's happening a lot because that's fast, but it's less accurate. And you see also more and more applications of using analog, so looking back in what we've experienced in the past, or using machine learning for this, which is in a way the same thing now. Now what can then be done is stochastic noise. So we can make one nowcast by extrapolating it, by adding growth and dissipation. But we can also say, hey, this is inherently uncertain, especially if we leave out all the physics. Let's make an ensemble out of that. And I'll show you later how that's done in steps, which is widely used. But there are multiple algorithms that does that, but you can make a full ensemble out of it and at least account a little bit for the uncertainty. Titan might be familiar to you. That's a nowcasting algorithm that's developed here. It's really focusing on storm tracking. And we've been working on PySteps, which is an open source Python initially Python setup of the steps algorithm. I'll explain that to you in a few slides. And right now it has become much more than that. It's kind of an open source nowcasting platform in which everyone can just put in their own nowcasting algorithm. So we can mix and match now, which is nice. And yeah, once you've done all that, in a set you can really cherry pick which of those steps you want to use and which not. You create the nowcast that you see on the right for the coming hours ahead. So here maximum 6 hours ahead. That's really pushing it. Typically we use it up to 3 hours ahead. So about the steps algorithm, that's one of the widely used nowcasting algorithms that is not directly tracking storms, but doing it on the entire 2D rainfall field that's coming from a rainfall estimate from the radar, for example. What STEPS is based on is basically past research from the late 90s, showing that the lifetime of rainfall fields is directly related to the size of the rainfall fields. So if you're looking at large-scale systems or stratiform rainfall, for example, they have a very long lifetime, and they tend to just move and not so much change. If you look at smaller systems, convective systems, for example, we all know they very quickly grow and dissipate, and the affection of that system is much less important. Now, STEPS basically uses that knowledge and takes it into account. So it takes the spatial rainfall fields, or kind of decomposes it in multiple spatial fields with a fast Fourier transform, and then assigns different lifetimes to these transforms. So if you see the top left here, the observed, then you can decompose it in multiple spatial scales. Could be 7 like here, but could be more or less than that. And the largest scale, level 1 here, that's just one large blob. That could be the stratiform field that you see. PyStep says, okay, that will have a long lifetime, so we're just going to affect it, and not much is going to change to that field. The shorter lifetimes instead, we know that's not going to affect so much. That's going to change a lot. STEPS started just stochastically for making ensembles. So what we do here is that we, on a short time scale, PyStep adds autoregression to basically make the field evolve over time, and then adds stochastic perturbations to make an ensemble out of that. So basically perturbations that can make rainfall cells either grow or dissipate stochastically, so it's just a matter of chance. The place where this happens is at the smallest scales. So that's where it's in a smart way applied. So we apply basically the stochastic noise and with that the uncertainty in the forecast to the smallest scales, and these are the scales where we have the least certainty of what is going to happen. So that is basically how that works. Now we've been looking in the past into, okay, if we use something like that countrywide, in the Netherlands in this case, I see here an example for the UK, by the way, what happens? How good is it? So we did a large sample analysis and we saw, well, this is kind of the standard look where in green you see the scale on the y-axis, on x the lead time, increasing towards the right. That the green line is nowcast, which starts at almost perfect scale because you start at the latest observations, hoping that they are good. And below that, in the dark gray line, you see NWP. Good thing of NWP is that it's very constant over time. And I'll show you later with actual validation that it pretty much looks like that, which is impressive, I always think. But the scale is much lower than the nowcasting in the beginning. And that has to do with, of course, you might be wrong in the physics, you might be wrong in your data assimilation, and multiple reasons. So nowcasting really adds for that first part. And that is, on average, we found, at least for the Netherlands, up to 2 hours ahead, where it is constantly better than NWP. After that, NWP starts to have a better scale than nowcasting. So that's why I said if you use nowcasting up to 6 hours, the system can calculate it, but it's really pushing it. It's not necessary. So we saw in this analysis that this scale is really based on what you do and where you are. So the rainfall type, it's not as skillful for convective systems as it is for stratiform systems, for example. We get a nice mixture of that in the Netherlands. The duration of the event matters. That is kind of coupled to the rainfall type as well. The location of the catchment, we did a catchment analysis here. So this 2 hours is really the small catchments focus, so not countrywide, but for all the small catchments in the Netherlands. And we saw that if the catchment is more downwind, we typically have southwesterly winds, you have a higher skill. So you have more wind information that you can affect into your domain. That is useful. If you're at the coast, all the way in the southwestern part of the Netherlands, your skill drops just because of where you're located. Catchment size also matters, and that's with almost every forecasting model. We're looking at a larger scale, it's a little bit easier to average out the errors, and that you see in nowcasting as well. Now coming back to this situation, July 21 in Europe, if I add the nowcast to it, ensemble nowcast in this case, you see a bit of a spread as well. You see that we're a lot closer to what actually happened. Still absolutely not perfect, but I would say there is a warning now at least coming up, and that is at least one box ticked. It might still not be perfect and there's a lot of work to do, but this is just to show you a bit what is possible. But we were not all completely happy with this yet. We wanted to go a little further than that. So the idea was if we have 2 hours of skill, but we know that for the first 6 to 12 hours, we actually have this predictability gap in precipitation forecasting that we really want to improve. We want to push these 2 hours a little bit further, and 2 hours is not enough. So how to improve it to at least, say, 6 hours ahead? That's where blending comes in. And blending is an optimal combination between nowcasting and NWP. It's also sometimes called seamless forecasting. And that's what I'm going to tell a bit about right now. How do we do that? How do we combine it? You could do it in a very simple and fast way, just linear blending. That is done quite often, actually. And the way to do that would be that you start with 100% weights for the nowcast. We know it's better for the first 2 hours. Then it drops very quickly, linearly to 0. And you do the opposite for the NWP. Works, is robust, is fast as well. But if I come back to that initial case where the NWP is quite far off from the observations, and that happens, what do you do with linear blending now? Because there is a point where you're here in the middle with 50% weights, where you're kind of smoothing out both of the extremes. And at least from a hydrological perspective, we wanted to keep those extremes because we knew in this case there was a flash flood taking place. So that's something we don't want. And that's where we get back into what we've been working on. So we've been extending the STEPS nowcasting framework into can we apply this idea also into blending, so combining with NWP. So the idea is that if we go back to this fast Fourier transform in which we had the rainfall decomposed in different spatial scales, can we then combine it per spatial scale? So basically assign weights varying in space and time, depending on at what spatial scale level you all are, because we know the nowcast has different levels of quality for the different spatial scale levels, but so does NWP. It's typically better at larger scales than at smaller. So that's what we've been doing. That's basically the start of the STEPS blending idea. So what we do is that we assign weights per component and per spatial scale. So the nowcast NWP and also the stochastic noise that we add for the ensemble, I'll get a weight, and those vary in time. So depending on when you make the forecast, NWP might be better now than it is in 2 hours from now. And depending on how good the forecasting products are also over time. So we do that per spatial scale level. Then so we blend everything per spatial scale. And then at the end, we combine it again. So we recompose it into one rainfall field. And then it looks like rainfall again. Because this looks a bit funny in a way. So to show you a bit what that looks like, and again, this is also going to be funny because we're still looking in this fast Fourier transform space. What you see on top is level 0. So these are the largest scale systems from the same rainfall system that you just saw. And at the bottom is level 4, so it's kind of the intermediate level size of rainfall fields. First column is the nowcast, second the NWP forecast, then we add noise to it as well. And it's very hard to make anything out of this. Most important is what the weights do. These are the lines that you see below here. So you see for the largest scale, and the nowcast starts with full weights. That's also what we hope to see, because the nowcast should be good at the beginning. But it also maintains that weight very long. For the reason that the nowcast, especially for these large scale systems that mostly affect and not so much change, should be quite good. NWP instead has 0 weight in the beginning, and it in this case slowly increases. And we add weight to it. If you're having a quick look at it, you also see that the weights don't add up to 1, but the square of them does. So that's how steps are set up. If we look at level 4, it looks even funnier in a way, but you see that in all cases, and in these cases, the NWP forecast was pretty bad. We see that the nowcast drops scale very quickly. It's only good for these small scales for the first half hour to an hour. And the NWP just does not get any weight. That's how painful it is for this case, but also kind of the reality given how bad it looked. Instead, we're just adding a lot of noise, so a lot of uncertainty to the forecast, basically. This is then the blended outcome. Still looks weird, but if we recompose it all, we end up with what you see here on the right. And that looks like rainfall again. That's kind of the blended end result. We see that we mostly keep a lot from the largest scales from the nowcast, from the top, and much less from the NWP forecast, but that comes in, especially for later lead times in the southwest. So you see that slowly coming in right now. That for blending so far. That was for the Netherlands. We've also done this in Australia. STEPS was originally developed by the UK Met Office and the Bureau of Meteorology. It was a shared project. And we've been working a lot with the Bureau of Meteorology to advance this together. So they've also been part of BiSteps. And what you see here is basically the same as what I've just shown, but then for the Australian system over Tasmania in this case. You see on the left radar, in the middle the blended forecast, and on the right NWP, where you already see that NWP is a touch coarser there. Just to show you another example. Now there's one more blending method I wanted to show you, because I also in the validation come back to that. While we were working on the STEPS implementation in BiSteps, another paper came out from Meteor Swiss, who were working on a more ensemble Kalman filter-based method. Inherently, blending 2 forecasts would be a Bayesian problem. You have 2 ideas or 2 predictions that are wrong. But together, you might end up with a better prediction. That's the idea of a Bayesian combination. And that's basically what the reduced space ensemble Kalman filter blending does. So it starts the way STEPS starts, so that's where it is nicely integratable in BiSteps. But I'm not going to go too much into detail here. But what it does is that it uses the nowcast as the first prediction, and then the NWP as a sort of a pseudo-observation. And then the Bayesian method in the Kalman filter starts to bring that together based on which one is closer at that moment. So you will see for the first lead time, so that still very nicely follows the nowcast. And with increasing lead time, you go into NWP. It's another way to approach it. It's, I think, a very neat way to do it in this way. I'll show you later also a couple of downsides of it. So that's why we're not using this operationally yet, but we're testing it. So coming back to the Dutch case, what we've been working on the past years is to operationalize this. So what we've been working on is implementing nowcasting, but also directly the seamless forecasting, by blending it with the Dutch NWP product, HARMONIE. It's an AROME-based model. And what HARMONIE does is that it's updated every hour. So we have an hourly update. It goes up to 3 days into the future, on a 3-kilometer resolution, or 2.5, I should say. And the radar data set is 5-minute interval on 1 kilometer. NWP data has 5 ensemble members. More is simply not possible at the moment, given the computer space they run it on. We run together with the Danish, the Irish, and the Icelandic in Iceland on a supercomputer. Nice and cool, but we have to share space, so that's the downfall of it. So we have 5 members, so what we do, we've been making nowcasts for 20 members, to at least have some sort of uncertainty estimate in the ensemble. We wanted to do that with the seamless forecast as well. So we wanted to get 20 members out of the NWP as well. What we've been making is a lagged ensemble. We've been looking back at also the past 3 issue times, including the current one, and that adds up to 20 members. The advantage is that, at least from past research, we know that the lagged ensemble gives a slightly more consistent view over time. So that might be a benefit. downfall is you're also working with an NWP that's 4 hours older than the most current one. Anyhow, what we currently have is that system. So we have a 20-member nowcast and we have a 20-member seamless forecast that both go up to 6 hours ahead. And the seamless forecast is after those 6 hours, 100% NWP. So you can just base the NWP forecast to it and continue from there without having to do extra calculations. So we've been testing that because that's something we've been missing also in literature, is just a long operational test of these kind of blended systems. So we've been running it operationally already for 2 years now, but we've done a more larger scale test over the past half year, July 25 till January 26. What we've been testing is for the Dutch system. I've never asked you, but I assumed you all knew about where the Netherlands is located, but it is about here in northwestern Europe. What we have in the Netherlands is 2 C-band radars. That's the one here at Den Helder and here at Herwijnen. And we have, at least in the past decades, quite nice neighbors. And we share the radar data. They also have C-band radars, and we've been trying to match up scanning strategies and whatnot to make sure we can make one composite out of that. So all of a sudden, we have 8 radars in the Netherlands, even though we only paid for 2. So that's pretty neat. So that is the system we use. The square-ish that you see here is the NWP domain of Harmony. So what we've been testing is the steps nowcast, the blending, as I've shown you, including a newer version. So over the past 2 years, we've also been upgrading steps towards an option that you can make it fully end up at 100% NWP. The thing with steps was it assumed that both forecasts were wrong and added uncertainty to it, which is theoretically the right approach. But it means that in 6 or 12 hours from now, you're still not 100% at the NWP forecast. And from a practical perspective, that was not ideal. So the operational meteorologists were not happy with that. So we thought, okay, we also make a system in which it's possible to linearly at the end dive into NWP. We've tested the ensemble common filter blending, the one I just introduced, also to see does that add anything for us, and then NWP is a benchmark as well. So starting with the start, this is what we started with in 2024. We just ran it for 1 week instead of the half year I just explained. This was a week with a lot of convective activity in the Netherlands. It doesn't happen that often in our climate, so that was a perfect test week for what we wanted to achieve. So what you see here, you see a spread, but I'm not going to go too much into detail there, but the thick lines are the averages of the CRPS, so the continuous ranked probability score. The lower, the better. So the lower that score, the better the error is. It's basically the mean absolute error, but then for ensemble predictions. What you see in light green is the NWP forecast. And as I already said, if we look at the validation later on, you see that it's a very nice horizontal line. And it is. So it starts with a relatively high error, but maintains it almost perfectly over time. In dark green, you see the nowcast. Starts with almost no error, increases rapidly, and then around 2 hours, just under 2 hours, it is just as good or just as bad as the NWP forecast. When we did this in my PhD, so it's a few years back, this point was still at 180 minutes. And the difference here is that we went from a 6-hour update cycle of Harmony to a 1-hour update cycle. So that's really beneficial in that sense. That's where we pushed it right now. Then in dark blue, you see the blended forecast, in this case only with steps. I will get to the ensemble common filter later. What we see is that it is pretty much constantly as good as or better than the individual forecast. And that is kind of what we hope to reach. The point from like 4 hours onwards is not statistically different, by the way. So I would say as good or as bad as NWP at that point. But before that, we really see the benefit of combining these two models. And that is also what made us already after that week decide, I don't think we need the nowcast by itself anymore. So we're just running the seamless forecast now. So that's the only product we give, and not the nowcast anymore. Now going into the full half year of validation that we've been working on, what you see here is again the average CRPS, but then over a half-year period. So that contains summer storms, but also typical Dutch stratiform winter drizzle, I would say. It's not the most interesting weather. What you see is on top of plots over the entire period, at least for days where we had a minimum wet area ratio, so a minimum amount of grid cells filtered rainfall of 1%. And at the bottom, split into the summer months on the left and the winter months on the right. What you see again, gray line, NWP, nice and stable. Then in the dashed gray line, you see the ensemble common filter blending, which goes a bit over the NWP in this case. And at the end, it ends with the same skill. So that is something that surprised us initially, because if we look at steps, both step setups, so black is what I explained, and black with the dotted black basically, is this adjustment where we just at the end go into NWP for the forecasters. You see that happening here. That's what we expected. But we were a bit shocked that the ensemble common filter blending, of which we really liked the idea, was underperforming, and for all seasons. And what we found is basically that this has to do with the spread of the forecast. So we noticed that the ensemble spread of the ensemble common filter approach was too narrow. That makes it not so useful for us right now, but we're working also with the German Weather Service on seeing what can we do to also increase that spread again, so that the ensemble is actually showing the uncertainty and not just a narrow band. Overall, you see that the steps blending forecast gives a bit that same impression we already had from that one summer week. It looks almost the same, which is very positive. So this is showing that that seamless approach is paying off. I'm going to skip this one. Coming back to the resulting discharge forecast for that flood case that you saw before, if we add the blending to it, at least the steps blending in this case, we get this forecast, at least discharge forecast. I cannot say whether the green one or the blue one is truly a better forecast. But in both cases, we capture the peak, and the blue one, in this case, the blending got a little bit closer. What we've been doing for the nowcasting is to really focus also on the hydrological predictability. We have some literature about that. For the blending has not been done yet, so that would actually be the next step. Can we also statistically show that the blending is useful for hydrological predictions? Or doesn't it make a difference compared to just having a nowcast and NWP? So that's an open question. I don't have the answers right now. So going to the very last part, going from this data-rich environments, the Netherlands, same in the US, to data-scarce areas. What you see here is a picture of Ghana, Accra. We're in the rainy season, a heavy convective system was coming in. You see the rain coming, and it also didn't stop raining for the following 3 hours after this happened. So there were some pretty severe floods that day. So the challenges we have in a situation like that is, well, I've just been talking about radar rainfall nowcasting mostly, but if we look at the radar coverage worldwide, it's very patchy. The US is well covered, southern Canada, Europe, eastern China, and that's where it pretty much stops. If we also look next to that at the actual on-the-ground observations from weather stations, this is for Accra. You see a couple of colored spots. These are the weather stations they have in that whole coastal region of Ghana. It's not bad, but it's not very dense either. So that makes it hard to, especially with convective rainfall, to know what fell already before even making a forecast. But the situation is quite challenging, especially when we go to Ghana, where these pictures are from, where in the rainy season it rains pretty much every day. So the soils are completely saturated. And we're talking about rainfall storms on a day that can bring up to 100 millimeters of rainfall. Nothing super extreme, also not by Ghanese standards, but on a saturated soil in a city, that's enough to really cause damage and severe flash flooding. Now, to also show you a bit the difference of what they're working with, at the moment in Ghana, they don't have their own NWP system. They run WARF, but not operationally, at least not at GMAT, the Meteorological Service. So what they started with was the medium range forecast of GFS in this case, because GFS is freely available. So on the right, you see the GFS forecast for a day with heavy convective storms and also flooding in Accra. And you see, so this is Accra, and you see basically on GFS for every hour in the lead time, almost the same pattern. It's kind of a medium amount of rainfall. It's never raining a lot, but it's always raining a bit. Statistically, pretty accurate. But for flash flood forecasting, it's not doing much. And if we then instead look at the meteosat observation, so that's one of the EUMET satellites above Africa and Europe, has in this case a 2-kilometer resolution and 10-minute update frequency, which is quite useful for real-time forecasting. Well, you see that it is not, the QPE of satellites is not perfect, and Meteosat certainly not always. So you see nicely the convective cells popping up. You see it flickering a bit. So that's where you see that the QPE is not perfect. But at least you see convective storms popping up, and that's quite a difference. So what we've been doing is using that for nowcasting with the same systems that I've been talking about. You see your two nowcasts, Steps and Linda. Linda also accounts for growth and dissipation that it observed in the past. And you see that, although not perfect at all, it's still nowcasting of convective systems. We're at least tracking convective storms now, and that is really for ACRA has been really a benefit, because for the coming hours we can all of a sudden say something about what is happening instead of it might rain a bit. So that is what we've been using. There's something else we're doing, not only in Ghana but other places as well. That is also alternative ways of sensing rainfall. That is with alternative sensors, and in this case commercial microwave links in mobile telephone networks. So when it rains, that attenuates the signal between two telephone towers a bit. But that is stored also by the telecom operators, because they want to know if their upkeep of the signal is good enough. So they kind of store what their signal strength was. If we have that, we can do the opposite. So we can determine back how much it rained along that path of the link. So that is basically what we're doing. So as it rains, you see a dip like this, and it's in the end, reverse engineering that is quite a simple mathematical solution. Oops, going one too far. Now we've been doing that is, we've been using that first in the Netherlands, and I'll show you later a system for Sri Lanka, where we've been using these systems also for nowcasting. Because if you have a lot of links, so in a densely populated area, you do have a lot of mobile telephone links. In fact, for the Netherlands, it is 100 times as dense as our weather station setup is, so this is quite useful. So all of a sudden you have a lot of observations. You can also make spatial maps out of that, and then you basically have something you can do nowcasting with. So we've been testing that. What you see on the left is a nowcast with the CML data, the commercial microwave link data, and on the right the reference. It's far from perfect, but it is doing something. So that was basically the start to also try that out in Sri Lanka, where you have a lot more challenges. They have a very dense network near the capital, Colombo. Here there are higher mountains, there's almost nothing. And then there are locations that are more remote, where the link lengths are very long. And then all of a sudden you start to make an estimate over 30 to 50 kilometers, and that's also not always saying much. That said, we can make pretty decent QPE, so rainfall estimates with these links compared to the weather stations that they have in Sri Lanka. So that was a good starting point. Then we also tried nowcasting there, and that becomes challenging because it's patchy. You see a lot of data gaps. The nowcasting algorithms really do not love that. And everything is ocean around Sri Lanka. So most of the systems move in, typically from east to west there. Yeah, you don't see it with just commercial microwave links only. That's where a radar would come in handy. And that is something that we're currently testing, but I don't have any results from that yet, is if we combine satellite information with these commercial microwave links, so basically do a bias correction of the satellite with these links, what can we do then? So that is what we're currently testing out, and I think that could be fairly interesting for data-scarce regions, where you have both data sets well present and not much else. So last thing to introduce, and that's also where the collaboration, at least between me and Aaron, come in, is so we've been working on Fuse ACRA, Fuse Early Warning System for ACRA. That's why I have so many pictures of ACRA. So what we've been doing, especially on the flood early warning side, is for both pluvial and flash flooding in the city, make a flood early warning system that is fed by satellite information, nowcasts, of course on-the-ground sensors, for as far as they're present, and then medium range forecast. So if we look at the meteorological information that goes into the system, is fairly limited. It's based on what is present. So we have the satellite-based nowcast, we have GFS, ECMWF they have sometimes, depending on whether they subscribe or not. WRF they run sporadically, and that's it. So what we currently miss is that gap where NWP would be really useful. And while I was talking to Aaron, they have a nice project running MPAS over West Africa, more from a climate projection perspective, of course. But this is where I think we can very nicely link up and see, does this also work hydrologically on that small of a scale? Because ACRA, of course, we go all of a sudden to the urban scale. If it does, I think we can make a good case to start trying this out in forecasting mode. And that takes a lot more work, of course, but that would be very interesting and I think also very impactful in the region. Because not only Ghana, all of these countries along the African west coast do miss a good operational setup of numerical weather prediction systems. So we can make a difference there, and we think it's going to help also on the hydrological predictability side, so where it comes into the few systems. So where can we collaborate? Well, that is one that I just explained. What I would also like to do is, if that works and we go into forecasting mode, I would like to try it out with blending, see if we can connect the satellite nowcast to an MPAS in the end. That would be really cool. And of course, I think there, at least now in the AI domain time, downscaling might also be quite interesting, both on the satellites, because that needs quite some correction anyway, and perhaps also on the NWP side. So that's where we can do some things as well. We've just some figures here. We've been working on some downscaling algorithms. It is promising so far, but it would be nice to test it in such a large-scale setup. So summarizing, and then we're done for today. I think flash flood early warning still needs enhanced rainfall information. What I've shown you in the beginning is that nowcasting is an easy win here. You can very easily, it doesn't cost much to run it, do better for the first 2 hours when it comes to precipitation forecasting. Then I've shown you that blending with NWP extends that skillful forecasting window, especially for the first 4 to 6 hours into the future. You really get the best out of both worlds there. But I would also dare to say it's still not enough yet. So if we really want to do better, we should see how we can improve both, and ideally together. And then, of course, and that's where I think where also collaboration options might come in, there are plenty of extra challenges in data-scarce areas, and that's where I hope to see also some potential for collaboration with you guys. And that's it. Thank you.
All right, questions for Ruben? Anyone?
I'll ask.
Okay.
Uh-oh.
You ready?
Sure.
Actually throwing hanger. Nice.
Thank you. Great talk. Interesting. Just like in your in the places where you're doing like in Accra, what is the community that you're working with, and how are you interfacing with them to use these forecasts? Dissemination. How are people seeing these things?
Yeah, good question, especially because that's a part of the whole warning chain that I left out of the story.
Yeah.
In Ghana, we work together with the National Meteorological Service, GMET, Hydro, that's the hydrological office, and maybe even more importantly with NOTMO, that's their disaster management organization. And NOTMO is set up that they have like a national, regional, and district level setup. So it goes hierarchically like that. So if they see something at national level, that's GMET, Hydro, and NOTMO together, then they start coordinating to the district levels and take action. That was not an easy process. Yeah. So we started together. Those three organizations knew each other, but had never worked together at the start of the project. All three very skilled, very good at what they do. So GMET can run those nowcasts themselves, know how to interpret them, know how to make warnings out of them. That was all easy. Hydro the same with hydrological models, NOTMO the same with disaster management. But getting that across those silos, so making that work, making GMET give the right information to Hydro so that they know what to do with the models, so that they can go to NOTMO. That has taken 2 years of trainings. The View system is completely helping with that, of course. It does almost all of that automated for them so that they can just look instead of run the models themselves. But it still comes to setting up procedures together. And we've been working on standard operating procedures together with all parties so that they know of each other, what the other is supposed to do, what they are supposed to do, and in what situations. So we have a cold phase and a warm phase. And in the cold phase, it's before something happens, just their day-to-day actions. The warm phase is, okay, something is happening. And one of the three organizations sees something happening. Then all three directly scale up to the warm phase, and then we have a protocol of how they should interact and share information. And that is working more or less. So So that is at least making a difference right now. But it is tricky. We notice, especially during the dry season. So once the floods are gone for a couple of months, the uptime goes down. So they're not looking as much at the system anymore. And then when the rainy season comes back, we notice whatever we described, they're not really doing it right now. So yeah,
Great.
long answer, but it remains challenging.
Questions? Yep.
So are you doing any radar DA with the HARMONIE NWP system, or is that just conventional observations only?
Good question as well. KNMI, so then the Dutch National Met Office is working on data simulation as we speak pretty much. It is working, so they're also going from a 1 hour time step to 50 minutes at the same time,
Cool. Yeah.
which would be pretty neat for what we're doing here. So far, the data simulation, at least on the precipitation side, is not super convincing yet. So I think that there's still some work to do. But that would be great. And I think something that we might still figure out, because yeah, there is an avenue of just assimilating things well in NWP, and then you don't need a nowcast, or combining them as we did here. Ideally, we go to something where the nowcast is ingested into the starting point of the NWP. And I know, at least I spoke to Ethan this morning, that this is being tested. We're definitely not doing that yet. So that's an avenue I would like to take as well.
Cool, thanks. Yeah, this is a really cool approach.
You have a
Glad
question?
I'm on the front row. Really interesting stuff. And I guess I'm thinking about the next step too, because you're a hydrologist, and so when you say there's flash flooding happening there, like in the city or in the country, and it's saturated, or there's a burn scar, as we have in the West now these days a lot. Are there approaches that you're taking to take that into account for the hydrologic part of the flooding, and or are there approaches out there that are effective in taking those kinds of surface variations into account?
Yeah, also that is a good question. Into the hydrological forecasting part of the spectrum, it depends. So if we work with our own models, we take at least the initial conditions into account, use data simulation as well in the hydrological modeling chain. So that helps with, if we're dealing with initial wet conditions and so on. So floods that come from that can account for pretty well. And when it comes to other situations, for example, burn scars, I don't think these are things we're accounting for well. Maybe not at all. I hope a little bit into hydrological models. I don't think we're collectively good at that at the moment, so that is definitely tricky. And then speaking from the Data-Scarce part, from the department where I work, we typically work with forecasting agencies all over the world, and typically use their hydrological models in their view system, because they know it, they can change it. So it depends on what they use. Yeah, so it's a bit a vague answer, but that's it could go either way.
Anyone else? All right. Well, if not, let's thank Ruben again.
Okay.